Okay, welcome people of the pre-seminar. Our speaker is Ben Bouwen, who's a local here in Prague, and he's going to give us some structural properties of C-star algebras, please.
Thank you, Thomas. Thank you for the introduction, and as always, happy to give a talk here at the pre-seminar. So today's topic is quite vague, maybe on purpose, but so the point of this pre-seminar talk is to give you an idea of two structural properties that will be examined in further detail in Tatiana's talk, namely quasi-diagonality and the MF property. And so the starting point is, okay, how can we analyze the structure of certain C-star algebras based on them embedding somehow in a nicer C-star algebra that we can understand? All right, but I guess as one might expect, it's so often too much to ask for a straight up embedding into a really nice C-star algebra like the matrix MIN matrices or something like this. And so there, for that reason, one of the starting points that I want to make is asymptotic star homomorphisms between C-star algebras. So what are these? So for now, I will only talk about discrete, but Tatiana will, I think, also mention continuous ones. So this is a sequence by n from a certain C-star algebra A into a sequence of C-star algebras Vn. And this is just a sequence of maps. These can be anything, set theoretic maps in full generality, such that they are asymptotically star homomorphisms. So in the sense that say linear. So what does this mean? It means that so if we have two elements A and B and a scalar lambda, then approximately in norm we can linearize this. So it's E, and this expression in norm tends to zero as n tends to infinity. Right. So taking the property of being linear and just writing it down approximately and saying that this holds A, B, and so at this point you can imagine what the rest of the properties will be. So a star homomorphism is a linear map which is also multiplicative. I'm not going to write down what this is going to be, but it's literally just the multiplicative property, but approximately, and then also star preserving. So meaning it preserves the adjoint approximately once again. Okay. Now, the interesting thing about these asymptotic star homomorphisms is that somehow if you impose additional exact conditions on these phi-ns themselves instead of just asymptotically, this can change the structural property that you end up with. And I guess morally, this can be thought of in the sense of if you do not require anything, then you don't, at least in the finite stages, you don't remember any of the linear adjoins, etc., structure that you have on the C-star algebras that you start with. Whereas if you already require this at a finite stage, then it somehow already remembers this. So for example, you can already require, so here, you can already require the phi-ns to be, for example, linear on the nose. You require them to be positive in the sense that they preserve the order on the C-star algebra. So if you have a positive element in the starting C-star algebra, then you still want this to be positive in the target. And another specific notion, which is slightly stronger than being positive, is what is known as completely positive. And this will also appear in Tatiana's talk later on, so that's why I wanted to highlight it. And this says essentially so that the map is will denote the CP for completely positive if not just psi itself, but also if you look at the matrix amplifications. So let's say, okay. So if you look at the k by k matrices over A, so phi epsilon, let's say from A to B, you can define an obvious map from the k by k matrices over A to the k by k matrices over B by just applying psi pointwise. So let's say a matrix Aij in A, map it to psi of Aij. Oops. And so we not just want psi to be positive, but we also want all of these psi k's to be positive as well. And so this is the kind of right notion of positivity in general to study. Now, maybe just a quick remark. Maps which are completely positive are star homomorphisms. This follows from them being positive, and also these matrix amplifications will then also remain positive. Then maybe a slightly more interesting class is if we have positive linear functionals. In particular, traces. So traces are positively linear functionals, which also satisfy the trace identity, namely that we can swap the entries of swap the entries in a product when applying the trace, as you do with the regular the canonical trace on the matrices. All right. And yeah, so somehow already requiring these properties on the nose at the finite stage in this asymptotic star homomorphism gives you some potentially extra structure. Now, as I mentioned in the beginning, we want to study these structural properties as having an asymptotic star homomorphism into C-star algebras that we understand better. So by that, I mean, in this case, matrix algebras. So Bn is M Kn for some. All right. And so this is where these two notions of quasi-diagonality and the MF property come in. So definition. A C-star algebra A is said to be a matricial field C-star algebra, which we will abbreviate as MF. If there exists an approximate star homomorphism, so and from A into the matrix algebras such that this is an approximate embedding. So in the sense that phi n are approximately, or sorry, I should say, I'm messing up. Should be asymptotic, not approximate. Such that they're asymptotically injective. So in the sense that the norm of phi n of A tends to A as n tends to infinity. Okay, this is, I guess, technically speaking, isometric, but for C-star algebras, being isometric and being injective is equivalent. So that's, I guess, the point of calling them injective. Okay, so yeah.
The multiplicative here is multiplicative on the nose. There's no asymptotic.
No. All of these are, they are asymptotically linear, multiplicative, and star preserving. Yes. Exactly. Exactly. Yeah. Right. And so, okay, this is this is our definition, right? This asymptotic injectivity corresponds to saying, okay, we still want the flavor of an embedding, right? It's not quite an embedding on the nose, but it's asymptotically an embedding. Right? And okay, now let me take a different color. I did not give myself enough space, but it should be fine. So now quasi-diagonal Caesar algebras, which we will denote with QD, is if this is true and all phi n are so completely positive and contractive. So in the sense that they are contractions as maps. In other words, they don't increase the norm. Great. Okay, now the question is, can we come up with some nice examples? Which Caesar algebras satisfy this sort of property? Which ones don't? And yeah, I mean, I think so, yeah. Well, yeah, I mean, so yeah, I guess I think typically the maps being completely positive also implicitly requires that they're already linear. Right, and obviously since they're already linear and on the nose, the asymptotic linearity is a superfluous condition. But okay. Any other questions?
If you get rid of asymptotically multiplicative instead, does that give you something else? Give you like another nuclear or something?
So if you get rid of asymptotically multiplicative, then and maybe also star preserve, but I'm not sure because nuclear also, then you also want maps going back into A. Right.
Right, but it was, yeah. Although someone's also saying that even one is enough, like even though it's not obvious.
Maybe. Yeah. It's definitely possible, but yeah, so nuclearity is also a property that can essentially be rewritten in terms of these asymptotic maps to an extent. Right. Now back to some examples. So, okay. Obviously, if you are already a matrix algebra, then you definitely have these maps. You just take the identity map and then you're done. But more generally, if you are what is known as AF, which means you are an inductive limit of finite dimensional Caesar algebras, then you will also be quasi-diagonal. And since it's pretty obvious that I can precompose phi n with any injective star homomorphism and still get this property, anything which embeds into any of these algebras also is quasi-diagonal, right? So if you embed into this an inductive limit of finite dimensional C-star algebras, then you will also be quasi-diagonal. And maybe something like slightly less trivial if you are a commutative C-star algebra. So you are the continuous functions over some compact Hausdorff space or locally compact, then you are also quasi-diagonal. This requires a bit more work, but this is also true. And then one final example that I wanted to highlight is cones. So a cone over C-star algebra A is defined as the continuous functions from which vanish at 0 from the unit interval into the C-star algebra A. And these come up quite prominently in this discussion because at some point in the 90s, Voiculescu proved that indeed these C-star algebras are quasi-diagonal, essentially through some as a consequence of the different results. But I will not go further into that. So the point is these, so if you just add on these continuous functions from C01, from 0, 1, then you also become quasi-diagonal. Okay. Now, I don't think so. I mean, separable maybe, but I don't think. I don't think that's required actually. Yeah. Yes. Yeah. Yes.
And then I'm thinking, okay, how the canon stuff was with by embedding the one, but other back and that. So any third.
Yeah.
I mean, the general one.
No, but yeah, you're right. This is for fully general. Okay. Yeah. Sorry. Yes. So yes. So they are equivalent. One way to see this is by an equivalent formulation of both of these properties. Essentially saying, and this is something that I wanted to mention anyway, so this is actually a good question. You can reformulate this whole asymptotic star-morphism business into, on the nose, embedding into the ultra power of, in this case, the universal UHF algebra Q. And so basically by using these maps as your approximate embedding and saying your matricial field is just saying you have an embedding into Q omega. Saying you are quasi-diagonal is saying that this embedding lifts to a sequence of CPC maps into L infinity of the universal UHF. And so by Choefros, if you're nuclear, then you will automatically have a CPC lift. And therefore, these are equivalent for nuclear separable. Okay. Okay. All right. Then maybe some quick notes to end. So I mentioned also in the abstract, there are some questions, obvious questions that you can ask about quasi-diagonality and the MF property. So as you can see from the definition, if you are quasi-diagonal, then you are MF. And if you are MF, then you are what is known as stably finite. So I won't go into detail into what stably finite exactly means. The point is this is a condition on the projections of your C-star algebra. It's saying that they're finite in the sense of, essentially in the sense of Mario von Neumann, how they defined it in von Neumann algebra. And so a natural question following these implications is whether the converse of these implications holds. So whether every stably finite C-star algebra is actually MF or quasi-diagonal. Both turn out to be false in general. So this this is untrue if you take, for example, the reduced group C-star algebra of the free group with two generators. This will be MF as a result of Horup and Torbjornsson, but it will not be quasi-diagonal as a consequence of result by Rosenberg. Right. So this is a counterexample. Then this also turns out to be untrue, but only relatively recently, essentially as a consequence of a negative solution to the Kahn embedding problem. So if you take a separable strongly extended C-star subalgebra with a unique trace, of M, where M is a 2-1 factor which is not Kahn embeddable, then this cannot be quasi-diagonal because that would imply that it embeds into Q omega, and therefore its completion, its strong completion would embed into R omega, but we just took M to be a counterexample to the Kahn embedding problem, so it shouldn't embed into R omega. Right. Yeah. I think there are some results. So I think if I recall correctly, yeah. I don't recall exactly what the.
There is no easy solution for I mean, easy to. Only for that school, only for that school, not the Okay, so it's very hard to understand why.
Yeah.
Some they use random variable. Probability.
Right. Yeah. But you raise a nice point that I wanted to end with, which is that this is not a nuclear Caesar algebra, right? So maybe one would hope is that if we add separable, stably finite, and nuclear, Caesar algebras, quasi-diagonal, or MF, since, as we discussed earlier, these are equivalent for nuclear Caesar algebras. And this is known as the black and dark curvature problem, and this is still open in general. So there are some results, namely your traceless in the right notion of not having traces, slightly stronger than just saying there are no tracial states. This is a result by Jamie Gabe. And then also for cross products by Z. So these are just Caesar algebras built up from a homeomorphism on a topological space X with X compact metrizable. But the fully general question is still open. Sorry? I think just the homeomorphism. Yes. Yes. So I should say, yeah. Sorry. Yeah, that's exactly what I was question. Yes. Yeah. So the question that I'm asking already. Yes. Yeah. Right. Yes. Yeah. So yeah, this is. I think you want faithful amenable trace. Okay. Yeah, that's true. Okay. I see. Okay. But yeah, so that's the question that I wanted to end with, and also by saying, so all of these properties can also be formulated as properties on for traces on Caesar algebras. So instead of asking the entire Caesar algebra to be traceless, one can to be matricial field or quasi-diagonal, one can formulate analogous properties for a trace on a C-stroll, and that will be also appearing in Tatiana's talk. But that was all I wanted to mention. So thank you for your attention.
Thank you, Ben. So we had some questions, but there's still time for more. So are there some questions from the audience?
Great.
Not off and on. Obsessive thing. So it's the question, you said stably finite is defined in terms of projections, properties on projections
Yes.
in the C-stroll. Does that mean then that it has like strong consequences for the K-theory problem?
Not necessarily. So it has you can still get any K-theory, any pair of abelian groups as a K-theory of a stably finite C-stroll. Yeah, well, don't you need, maybe stably finite is enough already to get an order. Yeah. Yeah, so maybe, yeah. I'm not 100% sure, but I think stably finite, yeah, might be enough for it to get an ordered. So you do get an order on the K-theory, but yeah, no, not in general, exactly.
And it's just a very naive question. You put separable in front of, where is it? In the question, are all separable
Yes.
stably? Does that mean quasi-diagonal are automatically separable or no?
No. But I guess the point of interest is mainly separable C-stroll algebras. But yeah, then you would take a net. Yeah.
Okay, so it's just a simplifying assumption.
To an extent, yeah.
An
But
extent.
I think there are some cases where you can already get results for general C-stroll algebras when you've proven them for separable C-stroll. So yeah. Yes.
More questions? Maybe I can.
Does Jamie, in fact, get AF embeddability in general, or right? Okay, yes.
Yes. So what he proves is essentially that all these notions, so AF embeddability, embedding into the cone over O2, all are equivalent in the setting of separable, exact, and traceless. So not even as strict as nuclear.
Yeah, right. Okay,
yeah,
cool.
Sorry? Yes, without UCT.
Maybe I can also ask a quick question. So in the definition here of the MF property, you're just saying you just want a sequence phi n with this property here.
Mm-hmm.
So let's say you find more than one. You have two of them. Can you say something about the KNs that you find there? So do they have to be kind of, is there some estimate? Or do they have to be the same, or could they be quite wild?
In general, definitely not the same. Typically, the sequence KM will tend to infinity because unless you are already a finite dimensional C-stroll algebra, somehow you need the entire you need a larger space than just matrices to find these sorts of maps. But I don't think there's a general like kind of way to bound the sequence of KNs in terms of some polynomial or something.
I see, because here, yeah, you are just asking to find such a sequence, but you're not asking that. They have some kind of universal property that every other sequence you would find would kind of connect to this one. Okay, you're not asking anything like that.
No, not quite.
Okay. Are there some questions from the online audience? Does not seem to be the case. Then let's thank Ben again. And now there's a short break and then we have the main seminar.